All right, so let's do another one with the comparison theorem. Again, you're only going to use this when the instructions say to. So find out if it converges or diverges, and you got to show your work and explain. So we're going to start with building our function. I know that cosine of x is smaller than or equal to 1, so that'll be a first good step. Divide both sides by the fourth root of x, and I get to here. Okay, so this is the function that's in my integral. That's good, and I have a new function. So now it's my job to take the integral and show all the work of taking that integral of the new function. So I'm going to take the limits of integration from the first problem, so 0 to pi, and I'm noticing there's no infinity, so there must be a vertical asymptote. Yep, there is at 0. So again, I'm going from 0 to pi, so I must be coming in from the positive side. And so t to pi, replacing the 0 with a t, and then rewriting this as t to the negative 1/4. And then, trying to write the positive in there. Okay, so then taking the antiderivative, add 1, divide by that same number, plug in the pi and the t. And so I guess I just skipped steps here. So limit as t goes to 0 from the positive side. So I'd have 4/3 pi to the 3/4 minus 4/3 t to the 3/4. Plugging in t equals 0, so that goes to 0. 0 to the 3/4 power is 0, so I get this. So that means that this converges. So since this integral converges, I have the two facts. I have the fractions compared, I have the larger one converging, therefore you just need to state the original integral converges also by the comparison theorem. All right, so let's try another one here. So let's do one with infinities, yes? So they're always going to be improper integrals, and it'll always say to use the comparison theorem. Okay, so this isn't anything I can build off of, very different kind of a problem. So what I'm going to suggest is that you write down the problem or the fraction that's in the integral. Notice there's no dx. I forgot to mention that earlier. No dx and no integral signs. No integral signs in the inequality, right? Because you can't compare integrals. So you just have to be bare bones fractions. So I wrote down the first thing. And then what I'm going to do is I'm going to write a new fraction or new function, and I'm just going to be taking off the number. So if I take off the number, because that's insignificant, it's also going to give me something that it's going to be able to integrate. I'm going to be able to rewrite this as x to a power to do the integral of. Okay, so this is the first step. So I've got the two fractions compared and no dx's, and I've got a new function that I want to take the integral of. So here I go. So 2 to infinity, integral of this. So first step is limit as t goes to infinity. Put the t in where the infinity was. And then taking the time to rewrite this, this is power over root, so that would be x to the negative 2/3. Then add 1 to the exponent, carrying the limit along every single time. Add 1 to the exponent, x to the 1/3 over 1/3 or times 3. And so finishing it off, limit as t goes to infinity. I get 3t to the 1/3, subtract 3 times 2 to the 1/3. Okay, so when I put in infinity, cube root of infinity, that's infinity. So we're done. It doesn't matter if you're taking off a finite number, right? This is infinity. Is that good? It is. Diverging is good because we're talking about the smaller one. So if the smaller diverges, that's good. So that means this larger one, the original problem, diverges also by the comparison theorem. Okay, so let's do one more here. I think that's it. Yes, okay, so let's start with this. Comparison theorem to show this. Okay, so cosecant squared is one I have a basic fact on, so I'm going to start with that. And then I'm going to take this and divide both sides by the cube root of x minus 1. This is still not something easy to take the antiderivative of, so I'm going to go one more step and take away the number. This will have more on the denominator, and so this is still smaller. I want to make sure that these inequalities stay the same. And I want to make sure, again, there's no dx in this integral or in these inequalities, and there's no integral signs. No integrals, right? Just bare bones fractions. Okay, so now it's my time to take the integral of this one using the limits of integration given in the beginning. So now I'm going to do limit as t goes to infinity, rewrite it as x to the negative 1/3, take the antiderivative, x to the 2/3 over 2/3, plug in the t, subtract off plugging in the 2. This gives me infinity, so this diverges. So this is good because this is the smaller. So if the smaller diverges, I can conclude, therefore, the larger diverges by the comparison theorem.